do today is to talk about functions and their inverses. And let's look at a mapping diagram similar to what we did some time ago. If I took some set of elements which we'll call the domain, and then another set of elements which is going to be called the range, well, let me take, say, some value x sub 1 and map it into some number, say, y sub 1, all right? And then let's pick out some element, say x sub 2, and map it into some element, oh, let's call it y sub 2. What I'd like to do is to take a third element, let's call it x sub 3, and map it into the same element of y sub 2, all right? Now, notice in the way in which we have set up this diagram, we have here two elements that are mapped into this one number of y sub 2. And the first question is, well, is it a function to begin with? Does this mapping diagram describe a function? And for each value of x, is there one and only one value for y, as we see it here in this mapping diagram? And I think that you will agree indeed that it is. Now, the difference between this function and perhaps another example that I'd like to look at is that we have these two numbers mapped into this one. In fact, we could have, say, an x sub 4 is mapped into the same number y sub 2. And the name that we give this is, the way in which we describe this is to say that we have a many-to-one function here, okay? As opposed to an example, now let's look at another mapping diagram in which here is our domain and the range. And let's take the element x sub 1 is mapped into, say, y sub 1, and x sub 2 is mapped into y sub 2, and let's say that x sub 3 is mapped into some number of y sub 3 by some function, let's call it f, okay? Now, notice in the case that we have here, each element from the domain is mapped into one element in our range, is that right? And if we call the first case a many-to-one function, what do you think that you'd like to call the second case, Glenn?
A one-to-one?
A one-to-one function, a one-to-one function, okay? Now, there's a nice, these two pictures, I think, illustrate this idea that's going to become quite important in this lesson. Now, let's come back to this first example in which certainly if we then were to take the element x sub 1 and map it into y sub 1, if we wanted to reverse that process and start with the number y sub 1, could we then end up with a unique value in the domain? And in the case as you see here, certainly y sub 1 would then be mapped into what number? But x sub 1. Now, in the second case, however, if we now want to take y sub 2 and map it into some number, the problem then is which number do you want to take? Either x sub 2 or x sub 1. In fact, when we reverse the process, what's your conclusion about that mapping? Is it a function or not? And Doug?
It's not.
In that case, it's not a function. Whereas in our second example, if we were to reverse the process of mapping y sub 1 into x sub 1, and y sub 2 then can be mapped into x sub 2, which is unique, and y sub 3 can be mapped into x sub 3, let's call the process going from, say, right to left a new function. Let's call it g, okay? And I think that you will agree that when we reverse the process, we end up with another function. Is that right? Whereas in the first case of a many-to-one function, we do not end up with a function when we reverse it. Well, it's that idea that I think that is going to be quite important to us. Let's make one of these, another schematic diagram. If you remember, we had this little function box. Let's put a button on it again. And in this case, let's take some elements which we're then going to put into this box. And let's think of this as an f function in which, suppose we put again the element x sub 1. And on the basis of our, say, our mapping diagram, what number then is going to pop out? But, Bill?
Y sub 1.
Oh, number y sub 1. If we put in the element x sub 2, we then will, when we press the button, the f function is then going to give us a number of, what, Dick?
Y sub 2.
Y sub 2, and of course, x sub 3 then is going to be mapped into, what? A y sub 3. If we were to think in terms of this set, we call this the set which is the domain of f. Let me use this notation. And then this set of elements is going to be called the what? This is the range of the f function. Now, what I'd like to do is to continue with the picture, another picture here, another one of these diagrams, in which in this case, let's have this number, which came out of the f function, go into this G box. And now, for example, y sub 1 is then going to be mapped into what element through the G function? And from our picture, our second mapping diagram done,
X sub 1.
it then is going to be mapped into x sub 1. Y sub 2 is then going to be mapped into x sub 2, and y sub 3, when it goes through the G function, is going to be mapped into
X
x sub 3. Now notice that we have here the domain of the G function was indeed the range of the f function. Is that right? So the domain of G is the same as the range of f, and similarly, here we have the range of G is equal to what? What can we say about that but the original domain of f? Okay? Now, notice the way in which we made this diagram. We started off with the f function, and then we had that element go into the G function. Now, we can just as well reverse the process. I don't think it's necessary to make that picture, but just sort of remove this first picture of the f function and repeat it down here, for example. All right? We then will have y sub 1 is mapped into x sub 1 through the G function, and then x sub 1 is going to be mapped into what number through the f function? Into y sub 1, which is the element that we started with. Isn't that right? And similarly, y sub 2 will be mapped through the G function into x sub 2, and x sub 2 then through the f function into y sub 2. All right? And I think then you will agree that in that case, we will end up with what? The range of f is then going to be the same as the domain of G. Is that right? In other words, we're going to arrive at the same conclusion. Well, let's actually look at a formula. Suppose we were to call the f function, let me just give it a name. Well, let's call it f of x is equal to 2x plus 3. And let's call the G function g of x is equal to 1/2 x minus 3/2. Okay? Now, the process of going through these function boxes from a mathematical point of view, from a notational point of view, is for us to say what then is meant by g of f of x. All right? That's really our composition of functions that we are looking at as we go through these through our function boxes. We then are going to take some number x and map it into some number y sub 1 in this case through the f function. And that's exactly what we have here. We'll take some number x and map it into f of x, which is the range of the f function. Is that right? Now, what then does this mean with respect to our notation? G of f of x. Well, what is f of x but 2x plus 3. And now when we look at g of 2x plus 3, we have 1/2 of, think of g of star is equal to 1/2 star minus 3/2, where star happens to be what number? 2x plus 3 minus 3/2. And now what then is this equal to? 1/2 of 2x is x plus 3/2 minus 3/2, and of course this then is equal to x. Now notice the number that we put into the original f function was x, and by this composition of functions, we ended up with indeed the same number x. Now let's reverse the process and look at f of g of x, all right, and see what happens. And here we have f of, now the g function is 1/2 x minus 3/2, so it's f of 1/2 x minus 3/2 is equal to, all right, now let's think again of f of star, where we have here f of star is equal to 2 times star plus 3. So it's going to be equal to what? 2 times 1/2 x minus 3/2, and now it's finally plus 3. Okay, now we have here twice 1/2 x is x minus twice 3/2 is 3 plus 3, and lo and behold, we end up with the same number x. All right? Now, when we have two functions f and g such that this statement is true and this statement is true, then in fact those two functions have a special relation with one another, and we call those functions what? We call them inverse functions. So let's write that down. F and g are inverses, all right? Are inverses if and only if f of g of x is the same as g of f of x, which is always going to be equal to x. And in fact, we want to say something about the domains and ranges, where the domain of the f function is going to be the same as what? The what? The range of the g function, and the what? The domain of the g function is the same as the range of the f function. Okay? Now this is our definition of what is meant by inverse functions. Now instead of calling the inverse of f g, there's another notational device that we write in which we say f is the same as g inverse. We use this little notation which looks like a g raised to the negative 1 power, but we will interpret that as an inverse. And in fact, we would also like to say that g is equal to what? F raised to the negative 1, or f inverse. All right? And anytime we have two functions which are inverses of each other, we may use this notation. Well, let's look at another idea. Suppose we were to write our function, our f function, say, if this is our f function, let's write it going back to the original case as we had there as an ordered pair. Okay, x sub 2 comma y sub 2, and then x sub 3 comma y sub 3 was our f function. If I then wanted to write f inverse, simply looking at our ordered pairs, how may we do so? A very simple way in which we can do that, Peter, is to
just switch them around.
just switch them around, in which the first element is now going to be what? Y sub 1 comma x sub 1, a y sub 2 comma x sub 2, a y sub 3 comma x sub 3 is then going to be its inverse function. Now, using the same idea, let's go back and talk about the particular example that we have. The f function was defined as what? Let me use the letter y is equal to 2x plus 3. Is that how we define the original f function? All right. And now, what I'd like to do is to, let's talk about f inverse as a set of all x comma y such that, and Peter said right up in here that we can switch them around from the f function with respect to ordered pairs. Now, how then may we write this formula right here? Phil?
X equals 2y plus 3.
X then is equal to 2y plus 3. We simply reverse our variables, and we now have x in terms of y. And that then is indeed exactly what you mean when you flip those ordered pairs. Now, let's look at this example, that is this function, this formula as we have it written here, and let's solve for y. And try to get y equals something. And just looking at that, and you say, well, let's see, now if I were to subtract 3, I'll have x minus 3. I then will divide by 2, and that then will give me y equals what? 1/2 x minus 3 halves. And lo and behold, if we come over here, for example, and look at our g function, that's exactly the formula that we have. Okay? So we can always, well, not always, but in many of the examples that we are going to be concerned with, you'll be able to find the formula for the inverse function by this interchange of variable process. Okay? Well, let's look at some graphs of these ideas. And suppose we were to look at a coordinate system in which we have the f function such that y is equal to 2x plus 3. And let's actually make their graphs and see what they look like. Okay? Well, looking at this, you know that it's a linear function. It has a y-intercept of what? 3, and a slope number of 2. So let's decide to run 2 and rise what? 4. 1, 2, 3, 4. And through those 2 points, we have a line which we may draw like this. And that then is going to be the graph of the f function. Okay? Now, let's look then at the inverse. Y is a 1/2 x minus 3 halves. The slope number is what? Negative 1.5, is that right? With a slope number of, that is the y-intercept is negative 3 halves, and the slope number is 1/2. So let's decide to run, say, 2 units. 2 units, is that right? And then we'll have to rise how many units? 1 unit, is that right? So indeed, right about this point is then going to be another point which is going to be on this graph. And if we were to make a line through those 2 points, it's going to look something like this. And here then is the graph of f inverse. Now, look at those two graphs, and is there any line about which you see some symmetry? Is there some line whose formula you are already familiar with, in which they are symmetrical? Brenda? Y is equal to x. So in fact, let's include that line on our graph, which we may, let me write that as a dotted line, and there then is the graph of y is equal to x. And now notice, for example, let's look at the ordered pair. Oh, it looks like 1, 1, 2, 3, 4, 5 must be on our graph. 1, 5 is on, say, the f function, and everything that we have said and what Peter has just said, therefore what other ordered pair must be on its inverse function? You know immediately, Doug?
5, 1.
5, 1. Well, here we have 1, 2, 3, 4, 5, 1, and sure enough, that ordered pair is on the inverse function. Notice, if we were to draw the line passing through those 2 points, what then is that line? What then is y equals x? The line formed by the equation y equals x going to do to the line joining these 2 points? And Bill?
It's going to perpendicularly bisect it.
It's going to be the perpendicular bisector. Very good. So if we took any point, well, let's call it A with coordinates of A comma B, all right, on the f function, on the graph of the f function, then the ordered pair associated, let's call this point over here, let's call that the point B, it will have ordered pair of what, Bill?
B, A.
Little b, comma A. And indeed, the line y equals x is going to be the perpendicular bisector of the segment AB. Okay? We have this symmetry across that line. Well, let's look at another example. Now, here I've already made a picture in which we have the function y equals x squared. Now, you know, we're all familiar with the graph of y equals x squared. It's this parabola. And the first question that you want to ask is this function, just look at this one for a moment, is this a one-to-one function or is it many-to-one? And perhaps, now, if you thought of all right, for this value of x, say, there exists a unique value of y. Is that right? Now, however, for that value of y, how many values of x do I have? And there are 2, so that when you reverse the process, all right, you do not get a unique value. In other words, what is your conclusion about this function right here? But that it is many to 1. Now, as soon as we say that it is many to 1, what is your conclusion about an inverse? And Steve?
It's not a function.
The inverse is not a function. In other words, therefore, the inverse does not exist, all right, as a function. Is the inverse a relation? Well, certainly it is a relation. And now, let's then look at the graph of the relation, which is then going to be this graph as we see it here. If you take the y equals x squared graph and flip it over y equals x and look at that symmetry, I think you will agree that we have this graph right here. Now notice that the formula for the original function y equals x squared, all right, is given to us here, but then the formula for this relation must then be what? Simply interchanging the variables, it's going to be what? X equals y squared. Now notice that that is not a function, because say for this value of x, we have 2 values for y, and that indeed excludes the case of a function. By the way, there's another very nice graph test that you can give a function to decide whether or not it is many to 1 or 1 to 1. Now we can think of a line parallel to the y-axis in order to decide whether or not it's a function. Is that right? And then wherever it intersects the graph, it must intersect it at one and only one point. Think only now of this y equals x squared. Now give it a similar test, what you might think of as a graph test, in which the line is parallel to the x-axis. And wherever it intersects the graph, does it intersect it at exactly one point? And I think you will agree that, in fact, in this case, it will intersect it at what? At 2 points. And so that, therefore, tells you that the function is many to 1, and therefore it has no inverse. All right? Now, what we can do, though, for this particular graph, and many people do so, is to limit the domain of the original function. For example, if you were then to say, let's let x be greater than or equal to 0, and just eliminate, say, this half of the graph, all right? In fact, let's look at a picture of that, in which we have it here in our next picture. There we have simply y equals x squared, where we took the domain of f to be greater than or equal to 0. X is greater than or equal to 0. Certainly its range then is also going to be values of y which are greater than or equal to 0. Now, if you then were to take its inverse function, think of it as being symmetric with respect to y equals x, you then are going to have only this half of the graph. And now notice the formula for that inverse function is y equals the square root of x, the positive square root of x. And again, now perhaps it's not quite apparent in this case, but the range of the f function is indeed the domain of the inverse function. But since they're all greater than or equal to 0, we have the same numbers in each case. Okay? And again, there is this nice symmetry about the line of y equals x. Now, let me give you your homework assignment in which you'll have an opportunity to think about these ideas.